practice, you do have to think about how many bits you need, because when you got a lot of them, it matters. It's terrible when you waste bits. It's even worse when you overflow the bits that you're playing with, especially if you don't notice it. So everything is fixed length. This is fixed length because it's length and offset. That's 2 integers. This is fixed length because whatever the length of field 2 is, however many bytes it is, that's what you store. This again is fixed length because although it's a variable length field, what you're storing is the length and the offset. And for field 4, again, it's fixed length because it's a fixed length field. The information about its length is in the catalog, and it's the same for field 4 of every single darn record you got. Every record has the same fixed length for field 2 and field 4. Not so for field 1 and field 3. That's why I have to store length and offset. This representation has the advantage that when it comes to the fixed length fields, I don't have to, I mean, often most of my fields are fixed length. So I don't have to mess around with having to store offsets for every record, for every field. I only have to store length and offset, and I do need both length and offset. I only have to store length and offset for the things that are variable length. So both of these formats are used in practice. Question?
So in this case, field 1 and field 3, since they both store the length as well as the offset, the length and the offset, the total size of those should be equal to the size of F2 and F4, correct?
No.
Because otherwise, how would we be able to calculate where F2?
Well, you have to do the calculation once, and you have to store it. Same as I said, you want to be able to store where each field starts. But if you want a field to figure out where, for example, where the information is for field 3, what you do is you know how long the stuff in this directory is for field 1, you know how long the stuff is for field 2, and you know whether or not field 3 is variable length or fixed length. So what you can do is you know where in this mini directory that's being stored, where the information about field 3 is stored. So you have to do that calculation once. You don't want to do it every time. But you go ahead and you do that calculation once, and you know where the information for field 1776 is. Because what you've done is you know how many things are variable length, how many things are fixed, how long the things are that are fixed. So you do that calculation once, and you store it in the catalog, and then you use it every other time.
So what you're saying is we would know beforehand what the fields are.
You know whether it's fixed or variable length,
Oh.
because that's part of the definition when you created the table.
Okay.
And that doesn't change.
Okay.
You don't go ahead and have a change from fixed length to variable length. No system that I know of allows that. Maybe it should, but it doesn't. If you did, then you'd have to do the recalculation. But that would be a big deal thing to do. Okay?
Thank you.
Everybody okay? Cool. Now you know how to do not only project 1, but parts of project 2. Maybe. There's a little bit more work that's going on. So again, the idea is, first of all, now don't confuse this. We're talking now about the pages. We'll be talking about 2 topics that people often confuse. We'll be talking about pages, and we'll be talking about records. Right now, we're talking about pages and what's going on there. But we will also be talking, we've just talked about how records are stored. Now we're talking about what's going on with pages. With pages, what you might do is have a list of, for a particular file, you have the header page for the file, which gives you, information like, finding, obviously, the pages, being able to seek and find the pages. And yes, you're going to be using fseek to find things inside this. So you're going to be, finding the pages that are inside the header, that are inside the file, and you might keep a list, rather than returning the pages, you might keep a list of free pages so you don't have to get them again. So once you've used a page, you might keep a list either on a per file basis or overall of all the free pages so you don't have to get pages again. And basically, the header page and the name of the file, all this stuff needs to get stored somewhere. You need to be able to store information about it. You might also store, and this is true inside project 1, you might store various statistics about how often you've read and written to the file and other stuff. So that might be information that you store inside a header page that you have for the file. And now here, what we're dealing with is that you're going to have 2 other pointers that you would be playing with in practice, which allow you easily to be able to go from page to page to page if it's stored as a list. You don't have to mess with all of this in project one. But if you were really implementing this in detail, you would want to be able to have easy ways of being able to find pages. Again, you're going to be taking advantage of the file system, for the Unix file system for project one. But in practice, you have just a linked list of all the pages inside the file, and you can always scan the file and find all the tuples that are inside the file. Okay, so this is there. So you have the 2 pointers for going forward and backwards, and you know there are things where here you're describing, and let me correct something that I just said. The full pages are ones where there's no space for any more records. The free page, the pages for free space, those are pages where, I'm not saying, and I misspoke, I said that the pages were free, they're not. These are pages that have some free space on them, which means you can put additional records on those pages. And again, in practice, this might be something that you would choose to do. And you might have more than one list. You might have pages with a lot of free space, pages with a little bit of free space. There are all kinds of clever ways, because what you want to be able to do is have a fast way of finding a page that can fit my record. As opposed to, you could always put every record on a different page, but that would be ugly in terms of the number of pages you have to look at. So these are not pages that are free, these are pages that have some free space on it. And again, you might have multiple different lists depending on how much free space there is on a page.
Question?
Yeah.
For previous slide, I'm a little bit confused on the topology of this. Does it, the header page, is there one page, or I'm sorry, 2 pages that only point to the header page, or do all the pages point to the header page?
The idea is that the header page points to 2 linked lists, and again,
Okay.
you have to go through all of them to be able to find all the records. But the notion is that you have a way of being able to find out when you ran out of things, because you have a way of getting back to the header page when you're done.
Got it. And there's a fixed amount of pages for both linked lists?
No, because pages get created and destroyed.
Right, that's true. Okay, thank you.
So in project one, the page file manager is the record, when you insert a new record or delete a record or et cetera, is the page file manager going to create a new file for each page and return that, or is
All the pages in a relation are going to be in a single file.
so the page file manager is just going to make one file and pass that back in a file?
And you're not going to be bothering to separate out full pages and pages with free space. This is just how things are done in practice. You don't have to mess with that. Again, you're going to be taking advantage of the file system. You're only going to be having one set of pages, and you're going to be using Seek to find it based on the page number, and you'll see how that works inside the labs.
Okay.
If you haven't seen how that works, it's actually pretty darn simple. It's pretty darn simple when you know how. As usual, everything's impossible until you know how to do it, and then it becomes easy.
Right, thank you.
When you see the solution, you'll see that it's relatively easy. The idea is to give you enough help to find the solution without giving you the full answer, which is why, you know, Saloni and Matthew have an interesting job to do in the labs to be able to make that work. So again, a file is a collection of pages. A page has a collection of tuples on it, and we'll see how you find a tuple on a page. Queries, again, have operators where deal with tuples, and you don't have to know how things are stored. You don't get to know how things are stored until you take this class, of course. And now, on each page, there is a notion of a bunch of slots on a page. And as I mentioned, a record ID is going to consist of a page ID and a slot ID. The page ID and the slot ID allow you to identify the record even when the record moves around on the page, or even decides to take a trip to Europe and go to a different page. Okay. So that's the idea. For each slot, there is a record. Page ID and slot ID, that's what an RID is. But I still haven't told you what a slot ID means, but I will. There are lots of other ways of playing with this. There are some systems in which the record ID actually, in some sense, corresponds to the primary key. And there's a primary key index, and you always find things by using primary key. So other indexes reference the primary key, and the primary key allows you to find the record. We'll be talking about RIDs using the notion of a page ID and slot ID. I'll talk about the use of primary keys a little more when we get into indexes. And again, there are lots of different ways of playing with this. I'm telling you about one way of doing this, one relatively old way of doing this. It's a good way of doing it, but there are lots of other alternatives. The property that you want is you want to be able to have the way of finding the record that's going to work even when the record gets moved around. Because otherwise your indexes and stuff having to do with concurrency control and recovery could end up getting messed up. And you need to find all the records, search, insert, delete, etc. So again, here's the general idea. You can go ahead and, there is a notion that you could use of having a directory which tells you about every single page inside the file. So what you can do is you have a directory where you have the information stored inside the directory. Instead of having a linked list, you have a full directory for every page, which allows you to be able to find page K. And it's an array, so you can get the information about page K, where you can, go to page K. And you also might have the information of how much free space you have on the page. And by the way, it would typically be a rough number of bytes that you have. Why would it be a rough number of bytes? Because if you keep it up to date, that's a lot of work. So keeping it up to date all the time, there's always a trade-off between having things fully consistent and the work that's required to do that, and being inconsistent but being, close enough to write to be able to get your work done. So basically what you do is have a directory which is a linked list of these things, because there might be a whole lot of pages inside a file. And so what you would do is you have an array. Here there are 12 things that you have, 3 times 4, and so data page 1, data page 2, data page 3, etc. And that would be for data page 13, would be in the second one, and so you can just find the information about it. And so basically you end up having the directory be a collection of pages, and again, there are all kinds of games you can play about the representation. This again is something that would be neat, because finding page K is something which you can just do via a calculation. It's just a calculation within these arrays to figure out which directory page to look at, and then which page within this. Which directory page you do a division, which position in the page you do a remainder. Right, so you do a division, -1, and you find out where things are. And the directory is going to end up, in some ways, being better than having the linked list of pages. The advantages of 2 different approaches. Walking a linked list takes a little bit more time. The directory, in some ways, ends up being, in some ways, a better way of finding things. There are trade-offs between the 2 approaches. Yeah.
What are the extents you have?
Yeah, the notion of an extent is going to be something where you have a collection of pages together, where you don't just allocate one page, but you allocate a collection of pages that's bigger than a page. So the things that you end up dealing with could be something which are larger than a page size.
Is that like the block file system?
It's related.
Okay.
It's a little, and there are other variations. Warning, on everything we're talking about, there are n different variations. So again, here's going to be something which is a straw man. This is just going to introduce us to what's really used. And so here's an idea that probably would occur to you as the first way of doing this, and it works, but not really. It works badly if you assume certain operations get done, like deletion. So here's a way of doing things. What you do is you have 3 kinds of information on a page. In the left, we're going to talk about the left-hand side, separate from the right-hand side. In the left-hand side, you say, okay, there are n slots on the page. So I'm going to pour the value n at the end of my page. Warning, in all the representations we're talking about, because we're having multiple data structures on the same page, you want to make sure that there aren't any head-on collisions. The wonderful thing about programming in C is you have control over everything you're doing. The terrible thing is you can destroy yourself very nicely and C won't stop you. You win some, you lose some. You have to be aware of all this when you're programming, doing systems programming in C. Java helps protect you. Java also doesn't allow you to do real system programming. Nobody does really low-level systems programming in Java. So here what we're going to do is we're going to say that there are n slots, and if we have fixed size records, we'll just have n slots. And you want to be able to find a record, then you've got your n slots, and you've got some free space, so in case you need another record, you can expand down as long as you don't clobber your number of records. And the things end up being, packed together. Okay, and that seems like a nice way of doing things. And now, the thing is that, the trouble is that this gets kind of interesting if you delete a record, because the free space is over here, all in green in one block. And if you delete a record, how do you know that you've got a free space if you're using the scheme? So the scheme has some disadvantages, because things do get deleted sometimes. So there's another approach that you could use where it's unpacked, where what you do is have the number of slots that are, available to you, which is M, and what you do is you have a collection of bits. Is the slot used or not used? 1 means it's used, 0 means it's not used. Okay, and it could be that you've only used N of the M things, and then you have a bunch of free space, after slot N. So you go ahead and use that, and that can work reasonably when you have fixed length records. But again, the record ID is going to be the page ID and the slot ID. Record ID, page ID, slot ID. So in the first alternative, if you have to move things around, then the RID isn't permanent, because the slot positions are fixed, okay? And the trouble is that packing changes the RID, which again, we said is unacceptable if we want the RID to be permanent. Okay, this is a picture that we're gonna spend some time on. And this is the picture that tells you what a page looks like. Now, don't confuse it. People often do. We spent time at the end of last lecture and at the beginning of this lecture talking about what a record looks like. And the records that we store here are going to look like that. Now we're talking about what a page looks like when it has a collection of records on it, where the records may be variable length. So the things on the previous slide would work nicely, at least the second one could, when things are fixed length, but in practice things are often variable length. And in project one, things are variable length. So how are we going to end up working with these things? We're going to have a slot directory, and it's a lot like what you saw already. We're going to have N at the end, which tells you how many slots there are on the page. That is, how many records there are that are on the page, or at least were born on that page. N is the number of slots on the page. That's in the last field of the record. Last word, that's on there, it's the last word in pages, it's there. And there is a directory which sometimes goes forward, sometimes goes backwards, and what we're doing here is going to go backwards. Sometimes people put it at the beginning of the page instead of the end. Hoo-ha, it's all the same deal. We'll talk about it being at the end. And there are going to be N slots, and what's inside every slot? An offset and a length. A length and an offset. Length and offset. That pointer, offset. So record 1 has length 24, and it's in, this arrow is not a pointer, it's a position on the page. It points to the record that corresponds to, oh, and sorry, this is number 1, I didn't follow the arrow properly. Here's the arrow for this. So if this is page I, then the record ID for this record is going to be I, 1. This is page I, so the record ID is page ID together with slot ID. Slot 1, length 24, that position there, it's going to be the record that has RID, page I, this is page I, and slot position 1. Here we've got something in slot position 2. Well, what's in slot position 2? Let's go behind the door and see. Slot position 2, there's something that is length 16, and is at that offset on the page, and if I can do a better job following the arrow that I did before, it's going to be this record. Position N, RID is going to be I, N. What's in N? Length 20, and it's going to be in that position. What does the record look like? Well, that's what we went over at the beginning of this lecture. That's what the record looks like. What does the page look like? This. So what you have on the page is a bunch of records on page I, and there are 3 areas on the page. Wait, I may be answering your question if you wait a second. 3 areas on the page. There's a place where you have records, there's a place where you have free space, and there's a place where you have this backwards growing slot directory. Now, what do you have to be careful about? 2 things. One of which is ubiquitous, and the other which has to do with the way this implementation happens to work. One of them is, don't have any head-on collisions on the highway. It's just not a good idea. Don't have a situation in which you end up having your slot directory colliding with your records. And you're responsible for doing that. Sorry, there ain't no magic doing it for you. You've got to write the code so that that works. but then there's this free space. So the free space is a buffer that's in between, although the free space could go down to 0. If it goes negative, then you've got that head-on collision that I talked about. But you're gonna ask me, what happens when a record becomes longer? Let's talk a little bit about that right now. Suppose that record 1, now for project 1 you only have to deal with in-service, so you don't have to deal with what I'm describing now. But suppose that record 1, which had been 24 bytes, had to become 26 bytes. Now let's assume that record 1 still fits on the page. There's 2 more bytes available on the page. Cool, but I mean, record 1 is somewhere, in the middle. There could be a whole lot. In fact, let me just take record 2 because it's easier to see what's going on. Record 2 had been 16. Let's suppose that record 2 becomes 30 bytes. Okay? Record 2 is in the middle of the page. The 4 bytes after it are being taken off by record 17 or something else. Here I've got all the actual records coalesced together in a bunch. So I don't have any free space in the middle. I've got all the records consecutively there. I can't put, taking it from 16 to 30, I can't put 14 more bytes in because I would overwrite. This is again something that C allows you to do very nicely. You can overwrite by putting the other 14 bytes in there. And C will let you do that very nicely. You're operating low level, but then you've clobbered whatever record happened to be there after record 2. Record 93 ends up getting clobbered. So there are various ways this is done in practice. For purposes of this relatively simple assignment, which you're not going to have to deal with until project 2, here's what you're going to do. You're going to take record 2 and make a copy of record 2. And you're going to copy all the things that are after record 2, I don't mean records 3, 4, 5, 6, etc. All the things after record 2 are all the things from here to the end of the occupied space. And I'm going to move them back. How many bytes am I going to move them back? 16. And if I do it right, all I've done is I've clobbered record 2, but I haven't clobbered the earlier stuff, and I haven't clobbered the later stuff. I've just moved it. And then I can put record 2 at the end because I'll have the space that record 2 occupied plus some of the free space available to be able to write it. I have the 16 bytes that I had for record 2. I'll have to steal 14 bytes from the free space to be able to write it, and I'll write it at the end. But there are 2 things that I needed to do that you may have thought were implicit, but if you're doing this as a systems programmer, you don't get to be implicit, you got to explicitly do it. Number 1, suppose that record 93 was after record 2. Record number 93's offset has just decreased by 16 bytes. Because I moved record 93 from this position to that position, right? Everything that appears after record 2, and again, I don't mean 3, 4, 5, 6, 7, 8, I mean all the records that appear later over here. All of them have got moved backward 16 bytes. So anything that was later, like record 1, its offset got reduced by 16 bytes because we moved it back 16 bytes. We didn't, mcopy, we moved all these things back 16 bytes. So that's one thing that I need to keep track of. And of course, I have to keep track of where record 2 is. So record 2 occupies a position. I have to set record 2's new position as well as its length. Its length becomes 30, and its offset becomes wherever I ended up putting it when I was done. And one other thing has to get changed. The information about the free space has to be corrected. Because the free space, which had, whatever, let's call it, say it had F bytes before, it now has F minus 14 bytes. And I need to know where it starts. So its starting point has moved forward by 14 bytes, and its length, the size of the free space, has gone down by 14 bytes. So let's just go over that very quickly one more time. How do I increase the length of record 2? This is not the only implementation. It's not an implementation that I would have in practice, but we're trying to make it simple for you in project 2. It's not required in project 1, it is required in project 2. When something becomes longer, move everything after it in the page back, because we don't want to leave any gaps in this implementation. Move everything back, in this case 16 bytes, because that's the length of record 2. And put record 2, assuming there's enough space for it, put record 2 at the end of the record space that's in the page. Having done that, I have to change the offset for all the things that were after record 2. I have to change the offset for record 2. I have to change the length for record 2. And my free space, assuming that things fit, because again, collisions are a bad idea when it comes to pages as well as on the highway. As long as there's enough space in the free space to do that, then I can do that. And if there isn't enough space, I have to move record 2 off the page, but that's another story that we will go into in more detail later. I've already told you a little bit about forwarding addresses, but we'll talk about that more another time. So, here's how I find the record. I have a permanent RID, which is the page number. The page number tells me you find the directory for this record, the slot directory on that page. And then I have the slot number, the slot ID. The slot ID tells me, where do I look to find the length and offset for this record? And even though I moved record 2 around, I have its length and its offset right there. More detail about moving it off the page to come later. Everybody cool? There's a lot of manipulation being done here, but you don't need C++ to understand that this is basic C kind of, bit twiddling. Not just bit twiddling, just basic coding questions.
Why is your directory backwards from the end?
Because if I want to have another record, I don't want to have to, have it go forward and have to mess with copying the whole directory. You can put it at the beginning instead and do it that way instead, but if it's backwards, I want to be able to increase it without, just by changing the value of n to n plus 1 and putting something here, assuming that there's enough room, that's all.
Oh, I see.
That's the only
Okay.
reason. Everybody okay? This is really important stuff. Now in practice, there's no reason why you might not have free space in the middle of the page. But then there's fragmentation. So, and it's a bit harder to be able to find all the records on the page, so we're simplifying it for you, but there's no reason why you couldn't have free space in the middle of the pages too. There's no reason why you might not choose to leave free space and periodically, when you feel like it, compact the page and move the records around as opposed to doing it every single time. This notion of being lazy. Being lazy can be a bad thing, and as a human trait, depends. Sometimes relaxing is good. But lazily doing certain things and only fixing things when it's worthwhile can be a good way of implementing a system. Taking care of everything immediately can be a performance glitch. Taking care of a whole bunch of lazy things, when it's worthwhile bothering, may make a little more sense. It depends. We're not going to go into the alternative representations. Okay, so again, variable length records, there are 2 variable size areas that are growing towards each other. This is, again, it's about the collisions. In what we're doing, again, 3 spaces on the page, the record space, the free space, and the slot directory. Not a good thing. Okay, so you have 2 areas growing with each other within a 1-page space budget. And there are all kinds of variations of this. As I mentioned, you could keep track of the free space holes and maybe compact periodically. You could end up using a totally different record format. There's something called PAX, which is kind of interesting. I'm going to be telling you about column-based storage. PAX is interesting because what it does is it stores records within a page, but it stores, within a page, it stores records by column. In other words, it stores inside the page, it stores the first column of each record, then the second column of each record, then the third column. So it's sort of a compromise between row-based storage and column-based storage. So there are lots of ways of doing it. Now we're going to talk about something really weird, which is picking yourself up by your own bootstraps. Computer systems have all kinds of interesting bootstrapping going on. What are the system catalogs? Well, the system catalogs are tables that tell you all sorts of wonderful information about tables, including themselves. Which means, by the way, that getting the system catalog started when there aren't any system catalogs requires a little bit of extra effort. But the system catalogs tell you about everything that's going on. For example, what you will do is, you'll have for each table, for each relation, we use relation a lot in this course because the textbook does, you'll have the information about what the name of that relation is and what file it's stored in. And you'll have information about whether it's stored as a heap or some other file structure. We'll talk about other file structures later in the course. You get information for each column, for each attribute. You'll have the name of the column, the type of the column, the length of it if it's fixed, the maximum if it's variable length. You'll have all kinds of information about that. If you have indexes, you'll have all kinds of information about the indexes. What the name of the index is, what relation it's defined on, what columns it's defined on, all sorts of other information about indexes. There's, in fact, information about so much stuff inside the catalogs. Yes, there's information about every constraint. But if you look in any reasonable, proprietary database system, even inside Postgres, which is public, there's all kinds of additional performance data that gets stored, which can help DBAs, automatic or human, be able to figure out how to do things. There's a huge amount of information that is stored. By the way, question, is the catalog information kept completely up to date every time something happens?
No.
No, it's not. It may be kept up to date in memory, but it doesn't get flushed to disk every time it gets updated. It doesn't get kept consistently. It's just not worth it. It's not important for these things to be approximate. And so, for example, for each index, it tells you whether it's a V tree or a heap or some other an R tree or something else, an LSM tree, which we're going to get to, tells you which fields it's on. It stores the view, but not the data in the view. This is the description of the view. Remember, a view is just logical, conceptual. It tells you what you have to do to get the values that are in the view, but it doesn't, unless you have a materialized view, the view itself is not going to be stored. And there's all kinds of statistical information, and again, the statistics are not kept completely up to date all the time. Things like the number of rows in a relation, approximate, the high and low value inside a column, the number of different values inside a column, the number of levels inside the index. All kinds of statistical information is kept. Authorization, who's allowed to do what to what. We didn't go into it much in 180, but there's these grant and revoke things that tell you who's allowed to do what to what. And those are, again, things that are stored inside the catalogs. And the catalogs are stored as record-based files too. And here's the kind of thing that they look like, where what you're doing is you're seeing students and faculty and the information about them, just some simple information. But you're also looking at things where one of the things that you have as a relation is the attribute catalog. And you have the fields, information about the fields in the attribute catalog inside the attribute catalog. So it really is bootstrapping. I am now out of time. What I want to do is to call out several people just to make sure that they can read